Welcome back. So after this first formal and very likely not so super intuitive explanation of what autoencoders are, let's just take a look how they work in reality, at least how it's done when using Python code. And here, first of all, not in reality, but with a fictional example, which hopefully helps. Okay, so let's keep it as simple as possible. So what I'm doing here is I generate two two processes, I would say, of features, so feature X and feature Y, and then I save them in a data frame, and I visualize it so that you can see here how it looks like. So basically what I'm doing here is using numbers between -1 and 1, 1,000 numbers between -1 and 1. Then I use the squared values of it, and here I multiply the first series with 0.5 and the second series with 2. And as always, I add a little randomness here because in reality we usually also have randomness. So and this is how it would look like. And now if we define an autoencoder as we're having in an original feature dimension, we have 2 dimensions, so 2 variables. We will try to bring the information given here by those 2 variables into a single number, okay? And maybe it's first of all important to understand what this means. So for the moment, let's assume we have simply the values of this data frame here. So we have, this is like the first column is the RDX values, and the second column are the values of the second variable here. So simply by math, if we want to bring this down, so we have here a shape of 1,000 times 2, 1,000 observations of 2 variables. If we want to bring this down to a single number for each sample, then we would simply need to multiply it with a 2 times 1 matrix. Okay, so let me see if that would work here. If we, for instance, simply add this, so that is what we would do. So if I simply would here each time I would multiply the value of the first variable and add it to the value of the second variable. This is how you can picture how we would bring the values of the first 2 variables in the first sample here into a single number. And as we know it from neural networks, we could add a bias term here. So we could add, I don't know, 0.1. So now 1, 1, and 0.1 would be the parameters of our encoder here. Okay, and obviously we also could use here a nonlinear activation function as we are used to do it for common hidden layer constructions that we use for forward neural networks. But this is how you can picture how our encoder works. So that is how we bring the information given of 2 variables into 1 dimension. We do this with a matrix operation, and which is in need of 2 or 3 or at least 2 parameter values. Okay, and obviously the decoder operation is the same backwards. So here we have now a 1,000 times 1 matrix, so to say. 1,000 because it's the sample size here. I generated 1,000 values here, and 1 is the dimensionality. And if we want to bring this back to a 1,000 times 2 matrix, then obviously we would need a 1 times 2 matrix. Okay, and this is like from simple math, really simple math, but just that you know what we are speaking of here. Okay, so obviously, it would be very likely enough to have like a single number here, which is maybe, for instance, going like this, and then we add certain values or a certain multiple of the single number and find the information that is given here, or that to recreate the X and Y variable here. So let's find out if our autoencoder is able to do that. So first of all here, I'm just using the values. I'm not using the standardized, or I'm not standardizing the values here or anything before, as we usually would need to do it. But as I know here that the variables are already on a similar scale because I constructed it in a way, I'm not doing this here. that we can directly use the original and raw data. Now, when it comes to defining the autoencoder in Keras, I think it's also super intuitive. So first of all, we define the first neural network, which is the encoder and which is responsible for bringing the original data with their dimensionality into the desired lower dimension. That is why we have here the input, which is given by 2. So that is like just the number 2. And then we want to bring those 2 values into the dimension of 1, and that is why we simply define here 1 layer. So this does the same thing as I showed you a few seconds ago, okay? But so it will have 3 parameters, and in the beginning those 3 parameters, they are randomly initialized, and then they will be fitted during the estimation process of the model. Now, if we have or maybe let me try. Maybe this works. I'm not sure. So if we would do this, not 100%. Yeah, it works already. So even before compiling. So this is if we define it here in the model, then let me take a look. Yeah. So even though before fitting the model and before compiling, if we define it here, that is our original data, but simply the values, then this is our encoder. Then what results, it initializes with certain random weights here. So that would be the first parameter. So each of those values of the x variable are multiplied with that. And each of the values of the y variable are multiplied with that, and always the bias of 0 is added, because bias terms are always initialized with 0, and the other ones typically with, I think, normal random variables. And then, so the first observation that you can see here, so if we call the predict method here, what it basically does is the same thing as I showed you before. So in order to generate this number, it multiplies the first value of x with 0.2 and the first value of y with 0.36, and then approximately this number results, okay? And that's done for all the numbers, and that's how you can picture. So this would be our reduced dimension of the 2 variables, but of course, this is just with random parameters, so it is not ensured that the information given in the 2 variables is really retained and is really condensed in a way such that if we know this single number, then we directly know a lot about the 2 numbers in the end again. And that is where we need to have also the decoder in the model, which does the same thing backwards. So it uses those values given here as input, and then with certain parameters, it regenerates or tries to regenerate, or in the first, simply by this definition, it brings back those single values to 2 values again, okay? And those 2 values then should represent the regenerations of the original variables x and y. And now, in order to make sure that the regeneration of the original data is done as best as possible, especially as best as possible by using the information of the lower dimensional representation, we are fitting a model with respect to the mean squared error of the deviations of the original data and their regeneration, okay? So that is why, so we have here the encoder with the sequential method of the Keras API defined as a neural network using 2 variables and outputting 1 variable. Then we have the decoder, which is a neural network defined using 1 value as input and making 2 predictions. Then we generate the autoencoder, which simply combines those 2 networks and sequentially, calls them in order to run through the autoencoder. then by the compile function, we are able to tell it to minimize the mean squared error of the original data and the regeneration. And then here we fit the data, and that is why we have the trait. So those are the features, and those are also the targets. Okay, that is what's how we can, tell the model, please use the original information of the data, then run it through the model, but please try to make the predictions of the model as close as possible to the original data again. Okay, so then we can click on that, and the model is going to be estimated. Let me just delete this here. And after it's finished, we can take a look. So obviously it learns quite quickly here, but let's leave it with the 200 epochs here. And then we can bring this down to, now the model has learned it. And again, if we call encoder predict of our original data, and flatten just already brings this to one dimensional array. Then this is the data. This is the reduced form of our original data. Okay, so in the beginning we would have our data train. So those are always the two variables here, so x and y. And for instance, to this first observation of the first sample of our data set, the reduced form which of a value which retains hopefully as much as information as possible of those two values is given here. And let's take a look at all these values. So if we do this and plot this here, then we can see, so this would be the reduced dimension of the two variables. And it kind of makes sense here, because you can see that the original data has this squared relationship here, and one of the variables is somewhere between 0.5 and 0, and the other is between 2 and 0. And this is, somewhere in between, I would say, a little bit more close to the y variable. The encoder weights that are given here after fitting the model. So if we want to regenerate out of this one-dimensional this one-dimensional representation of the original data, the first variable we always multiply this value that we have here with this weight and add this bias term. And now we can take a look how this works, so if this works, and we can see that it almost works perfectly here. Okay, so we have the x is the blue line here, original data, the green line will be the regeneration. Y, the original one is orange, and as you can see, the regenerations are also given here. So what basically the autoencoder learned here is it would be enough to memorize those values here in order to regenerate the original data, because the original data has many similarities. It has a quadratic form here, and basically that's what the autoencoder learned here. What also can happen if you call this more often, each time we compile a model again and again, it always initializes the model with different bias and weights in the beginning. So it does not necessarily has to be this case as you could observe it here each time. Sometimes, okay, this time again it looks similar, but sometimes it could also would be reasonable if the reduced dimension would be, like this one mirrored at the x-axis or at an axis that you can picture here, because even learning that we have this squared relationship would be an analogy also that learning that we have, for instance, a relationship that is like this here. So we only then would need negative weights, and we could also be able to regenerate the data. Just as I see it here, each time you try this on your own, each time please also again call this first one here, because I'm writing the regenerations in the data frame at a later step, and that was the problem that we had at the second. So let's just try this one more time here. And as always, you are very welcome to play around with the code by yourself, because that's, I think, where you learn the most. And let's take a look. Okay, yeah, looks again similar, but I would guess now that the returns are not as good as before. Okay, they are as good as before. Okay, and just one more thing, if you are in the code here, you can also check if, because if we now get a little bit more, I would say, mean to the autoencoder, because that was kind of easy, and what we used here was an autoencoder, which I would refer to as the linear autoencoder, because we used no nonlinear activation function. But now, for instance, if we replace this squared version here, so let's just use the, for instance, sinus of the inputs, and sorry, 0.5 times, and let's just copy that here, and the cosinus. So if we get more, if we become more complex, and let's just go here from -3 to 3, so that kind of gets mean for our linear autoencoder, because these are really high nonlinear relationships. And here my experience is that it fails to really regenerate this kind of behavior. So let's do this one time with the linear autoencoder that we used before, and take a look at our reduced dimension, how this looks. Obviously it will look different to that one. So here it basically, let me take a look at the regeneration. I would say, yeah, so at some point it decides that it's not able to regenerate both, and then it focuses on one of the two forms here, so on the sinus or the cosinus, and that is what you can see here. So here it almost succeeds in almost perfectly matching the original data of the x variable, but it fails in regeneration of the y variable. So, and I would say that's what needs to be, or what I expect here, because as I said before, this is a very, I would say, for a computer, complex nonlinear relationship to learn here, even though it, or kind of depends, but for this setting here, it's complex to learn. So what we can try, or if you play around with the code, you can try on your own. If you uncomment this, then this turns into a stacked autoencoder with, first of all, 10 neurons in between and a nonlinear activation function. So let's try this. By experience, I can tell you right now, it also does not succeed in perfectly regeneration or in a perfect regeneration of the original data, but it's getting more and more better. And if we really would to, you know, have the best possible regeneration that we can have here, I would guess that it takes a little more, but as you can see, this model is already more complex, meaning has more parameters, has nonlinear versions. But as you can see here, it's getting way more better, but something's happening here on the left, on the right, where it's confused, I would say, by that we have here the x variable and here the y variable. But nevertheless, I hope you can see the effect. It's getting better again when we using a more advanced definition of an autoencoder, also including nonlinear activations. And that is what we need when we have a very complex and nonlinear functional form here. Okay, but for the moment, let me just bring this back to our original example. And then with the help of this video, I would highly recommend to you, as I say always, to do this on your own and to play around with this on your own. Also, some of the, or the code, how you could define an autoencoder, and also how you could define an autoencoder for sequential data, for instance. So for a recurrent autoencoder or convolution autoencoder is what you can find in the hands-on machine learning book, which I always can recommend to you, especially when you want to have also some good examples to start with. And yeah, but the rest is on you. I mean, I fully understand that in the first, at first sight, this kind of seems odd. Yeah, okay, now we're having something like this, but I still would guess that the regeneration is again quite good. Yeah, as I said before. So yeah, in the beginning, this all may sound not very super intuitive and kind of strange to you, but as out of personal experience, the more you think about it, and the more applications you see, the more intuitive it gets. And at a certain point in time, at least from my own experience, I would say it getting super intuitive. And the longer or the more time I spend with it, the more all real-world applications come into my mind, or the more real-world applications I've also seen. So autoencoders are way more important than they may look at first sight. So that's why I'm spending 3 videos here at this topic, because I think it's kind of important, especially also it's something different to the things that you usually do in the beginning, because in the beginning you usually build some networks that are made for making good predictions, and this is something different. And this also shows this is like a first architecture which I would say is kind of creative, and in a very creative way does something different in order to achieve something different than simple predictions here. And that is what I really like about neural networks, that they are not only suited for the classical prediction problems, they can be used for so many more things when they are constructed in creative ways. And yeah, that is what I really like about them. And in the next video, I show you how a simple linear autoencoder can be used by you to build your own exchange traded fund. So I don't know, grab a coffee, get a break or make a break, and then come back and see the next video. Bye bye.